How do you go from a logic diagram to an actual circuit? Stay tuned, because today we'll be going over how I turned this CPU logic diagram into an actual circuit with transistors. Hello everyone, my name is Mike and you're watching Polymath Unlimited. Those of you who have been following me for a while will know that over the past year or so I've been documenting the design work of an 8-bit CPU in Logisim. The goal of this project has always been to build this CPU out of real transistors at some point. With the design work pretty much done, there's only so much more we can do in Logisim before we get to work trying to accomplish this goal. However, there is one more thing we can do in Logisim that will be a huge help to us for the physical build. Right at the very beginning of this project, I made an episode detailing how to build logic gates out of physical transistors. It turns out Logisim has a very handy transistor component that makes it very straightforward to simulate NMOS circuits. Ever since I discovered this feature though, the question I've always had was, can you make a whole CPU from transistors in Logisim? Turns out, yes, you can. Over the past week, I have painstakingly reconstructed the entire logic diagram for the Chameleon CPU into transistorized NMOS in Logisim. I did this for a couple of reasons. Firstly, it is freaking cool. I mean, just look at this. You can't tell me that it's not satisfying to be able to physically see almost 2,000 transistors all working together to run an actual program. Secondly, building the NMOS circuitry in Logisim will help verify the design before I actually build anything for real. It would be a shame to go through all that work building a bunch of physical circuitry only to find out that it doesn't work at the end. Simulating the CPU at the transistor level in Logisim will help avoid that. And finally, building this NMOS version of the CPU allowed me to test out some hardware optimizations I've been planning on implementing. For example, the address registers and the instruction register are now asynchronous, meaning they can be built using simpler circuitry than a synchronous register. I used a similar technique for building most of the registers in my Sublex CPU that I built last summer. I'll put a link to the video I made about that processor in the description if you're interested. Anyway, how did I manage to convert the entire CPU diagram into transistors? Well, just like we did when we were designing the CPU's logic, I started with the ALU. If we zoom in on the ALU and compare it side by side with the logic gate version we built earlier, it should be fairly straightforward to see how it was done. We can see the NAND and XNOR gates that are responsible for enabling the A operand and inverting the B operand, respectively. We can also see the Chameleon gate, which is responsible for both selecting and performing a given ALU operation. The only difference here is I changed the AND gate to a NAND gate, and I changed the NOR gate into an OR gate, which allowed me to change the final NOR into an AND. This allowed me to simply connect the outputs of the two gates together instead of explicitly building the final AND gate, which saved me a lot of transistors. I used some similar tricks when building the final XOR gate / multiplexer combination, which handles carry inputs and bit shifting for each ALU slice. I also used the same trick when building the ALU's carry look-ahead unit. Taking a look at the ALU flag generators, we can also see the NOR gate responsible for zero detection, the multiplexer responsible for carry detection, and the XNOR gate responsible for overflow detection. It was then a simple matter of just hooking together a bunch of NAND gates to form the ALU's operation decoder. Once the ALU was built and I had verified that all of the ALU operations were behaving correctly, it was time to start building the registers. I started by building a simple transistor-based SR latch. Adding one more transistor allows the set and reset inputs to be selectively enabled. Connecting two of these together with a clock and inverted clock signal creates a master-slave flip-flop. Adding 8 of these flip-flops to the circuit allowed me to make the accumulator. I allowed the accumulator to output to the bus by connecting it with some open-drain NAND gates. I also built another 4-bit register to store the ALU flags, very similarly to how I built the accumulator. Then I added the 2 address registers, each built of some single gated SR latches, since they didn't need to be synchronous. Instead of building D latches, which would have required one additional transistor per latch, I decided to save some transistors by adding a second bus which simply always took the inverted value of the data bus. I also created the address bus the same way as the data bus and allowed the address registers to output to the address bus through some more open drain NAND gates. The program counter is pretty similar to the accumulator. The only difference is that it has an incrementer circuit built in to allow it to count through the address space. This incrementer was made from some modified XNOR gates, allowing me to incorporate a full carry look-ahead unit for both bytes of the program counter in a surprisingly small amount of transistors. I also added an additional transistor to each latch in the program counter to enable me to hook it up to a reset signal. The program counter can output to both the data bus and the address bus through more open drain logic. The stack pointer is very similar to the program counter, but it has a circuit that can both increment and decrement, meaning that it needs an extra XNOR gate to handle the decrementing. I also added some carry look-ahead logic to help speed up the incrementer-decrementer circuit. However, due to the way I inverted some logic elements, I was able to build the carry look-ahead logic using OR gates instead of AND gates. The instruction register is basically identical to the address registers. It is simply an asynchronous register with its value being sent to both the ALU's opcode decoder and the instruction decoder. The step counter is very similar to the program counter, just smaller and with some simplifications due to some program counter features that it doesn't need. Its output also goes to the instruction decoder. The instruction decoder is more or less a faithful reproduction of the logic diagram. I figured I didn't want to try to mess with this circuit too much since it works, and it was already pretty well optimized to begin with. The most notable difference between this NMOS version and the original logic diagram is that some control signals get disabled when the clock is high. This is because I made some registers asynchronous in this version. If I didn't disable the control signals related to these registers when the clock is high, then there would have been a risk of running into race conditions. This is because immediately after the leading edge of the clock signal, many signals in the CPU will still be stabilizing and will therefore not contain correct values. If some of these incorrect values accidentally cause an asynchronous register's input enable signal to go high, then garbage data might be loaded into that register, which would corrupt the entire execution sequence. Disabling the input enable signals for such registers while the clock is high is a simple but effective method to eliminate that possibility. I already did this anyway in the original logic diagram for the RAM's read and write signals, since the RAM is also asynchronous. So it was a fairly straightforward thing to add more such logic here to protect the new asynchronous registers. The boot circuit is also more or less a faithful reproduction of the original logic diagram. Two latches determine whether the CPU is in boot mode or run mode. When in boot mode, the CPU simply copies the contents of ROM into RAM, and the CPU can be placed into boot mode by pressing the boot button. The CPU can also be reset or be taken out of boot mode prematurely by pressing the reset button. One thing that I did add here that was not in the original logic diagram was this latch that detects stack overflows. If the stack pointer ever counts down below 0, or if it ever counts up above 55, then the latch will change state and the stack overflow indicator will turn on. I figured this would be a useful thing to have moving forward, especially on the physical build, since it will allow us to detect stack overflows very easily. The one area where I cheated a bit and used pre-built logic gates instead of transistors was in the I/O devices. I did this mainly because I'm not necessarily planning on building these I/O devices completely from scratch like the rest of the CPU. They only need to be mapped to certain memory locations, so these gates handle that effectively. With the CPU finished, let's try running an actual program on it. Unfortunately, this is a bit less straightforward to do here than it was in the original logic gate only implementation. For some reason, something about the transistor component makes it so that Logisim freaks out when the circuit first opens due to oscillations. I suspect this happens because of the latches we are using. They simply oscillate between states rapidly without settling into a definite state. Since many of the latches are not hooked up to a reset signal, there is really no easy way to break out of these oscillations. Luckily, I was able to come up with a fairly straightforward workaround. When we open up the circuit, we'll go to Project Options. Then we'll set iterations until oscillation as high as it will go, then check the Add Noise to Component Delays box. Now we can reset the circuit by pressing Ctrl-R, then While holding the reset button down on the circuit, we enable the simulation by pressing Ctrl E. This will make it so that all of the latches connected to the reset signal get placed in a definite state. Many of the other latches will still be oscillating though, but since we have added noise to the component delays, we can simply re-enable the simulation by pressing Ctrl E again. Some latches will still be oscillating, but there should be less than before. Now we can simply keep pressing Ctrl E until all of the latches have settled into definite states. I have found that if we keep the noise enabled, then some aspects of our CPU's timing will get thrown off. So after all latches have settled, we'll go back to project options and reset them to the default settings. Now we can copy a program into our CPU's ROM. I have simply copied the Pi computing program we wrote a couple of weeks ago. If we press boot, wait for the program to load into RAM, and then press reset once it has, we should see that the program runs just fine. It does run a bit slower than the Logisim version. It turns out that Logisim runs into some bottlenecks when trying to handle almost 2,000 transistors on the same circuit. But if we run the program for a while, we should see the first 5 digits of Pi get printed to the console. Well, we're at a really exciting point in the project. With this new Logisim circuit, we are ready to start actually designing the physical circuitry. Earlier this week, I put out a poll so that you guys could help me decide which approach to take during the physical build, and the results of that poll seem to indicate that you guys would prefer a PCB build. So we'll get started designing some PCBs in KiCad soon. Until then, feel free to play around with this circuit. I've uploaded it to my GitHub, and I'll leave a link to that in the description if you want to check it out. Thanks for watching, thanks to all of my subscribers, and I will see you next time.